Madam, very good evening, madam. Good evening, madam. Madam, good evening, madam. Madam, good evening, madam. Madam. Dear participants, my voice is audible to everyone.
Yes, sir. Audible, sir.
Yeah. Thank you, sir. Thank you. Thank you very much. Madam, good evening, madam.
Sir, good evening, sir.
Madam. We are very happy today on our FDP program for your valuable contributions. We are awaiting for your session, madam. Really, we are awaiting for your session, madam. Thanking you for your joining for our ATAL sponsored 1-week faculty development program on quantum cryptography enabled autonomous underwater vehicles, madam. Very warm welcome to you, madam. We are from the Department of Computer Science and Engineering. We are organizing this ATAL sponsored 1-week faculty development program, madam. Thank you, madam. Thanking you for your valuable presence, and we are awaiting for your valuable deliverables, madam. Thank you, madam. Ma Ritika?
Yes, sir.
Yeah. Kindly introduce our respected professor and Dr.S. Bhagavathi Priya, madam, who is working as a Amrita School of Computing in Amrita Peetam, Chennai. Kindly introduce, ma'am.
Yes, sir, sure, sir.
Thank you, madam. Thank you.
A very good evening to one and all present here. Today we have the pleasure of hosting Dr. S. Bhagavathi Priya, ma'am, a distinguished associate professor at Amrita School of Computing, Amrita Vidya Peetam, Chennai. With over 26 years of experience in teaching and 15 years in research, Dr. Priya, ma'am, has established herself as a leader in the field of computer science and engineering. Ma'am is a gold medalist in her MTech. Dr. Priya ma'am has earned her PhD degree from Jawaharlal Nehru Technological University, Hyderabad. Her research endeavors have led to numerous publications in esteemed conferences and journals as well. And ma'am has also authored a book on operating systems. As a dedicated mentor, Dr. Priya ma'am has guided 9 research scholars to success. Her contributions to academia have been recognized with several awards, including the Best Paper Awards at IIIT-SriCity 2015 and CAASR International Conference 2017. Ma'am also has been honored as one of the top 20 influential women educators in Tamil Nadu. We are delighted to have Dr. Priya ma'am with us today and share her expertise with us. Let's give ma'am a warm welcome. We cordially welcome you, ma'am.
Thank you, Maritika. Thank you. Madam, now we are going to hand over the session for our respected today's resource person, Dr. S. Bhagavathi Priya, madam, Associate Professor, Department of Computer Science and Engineering in Amrita School of Computing, Chennai.
Thank you, sir. Thank you for the nice introduction and the warm welcome. First of all, I thank Chandrakant sir for inviting me as a resource person for this ATAL FDP quantum cryptography enabled autonomous underwater vehicles. So I thank Chandrakant sir once again and Vamsivardhan sir. Sir, shall I start my session, sir?
Yes, madam. Thank you, madam.
Okay.
Thank you.
I'll share my screen.
Yes.
Is it visible, sir?
Yes, it is visible, madam. It is visible, madam.
Okay, sir. Thank you, sir. Okay. So today's session is about classical versus quantum computing in the technology perspective. So I am Dr. Bhagavathi Priya, working as Associate Professor and Program Chair of Amrita School of Computing, Amrita Viswa Peetam, Chennai. So first we'll start with quantum computation. So as you all know, we are using the classical bits, zeros and ones. As a computer engineer, so we all know the classical bits, zeros and ones. Normally we are using this zeros and ones. Is it visible, sir?
It is visible, madam. It is visible, madam. Please
Okay.
continue, madam. Thank you, madam.
But it is not visible for me. Once again, I will check, sir.
Sure, madam. Sure, madam. From our side, it is very clear, madam.
Okay,
From
sir.
participants and also it is clear, madam.
My side, it is not visible. I will check it once again, sir.
Yeah, sure, madam. Sure.
Yes, sir. Yes. Now it is visible. So, in the classical computer, normally we are using zeros and ones. Okay. So,
Madam,
we are
please.
operating all these processes using these zeros and ones.
Madam,
Normally, we represent the numbers using zeros and ones. For any information we want to convey or using the machine, we have to use zeros and ones or in the form of zeros and ones.
Madam,
Where-
please, madam. Madam, we are not getting your screen, madam.
Oh,
Yeah, madam.
1 minute, sir. 1 minute.
Yeah, sure.
Is it visible now, sir?
Now it is visible, madam.
Okay, thank you, sir.
It is visible, madam. Thank you, madam. Thank you.
So when you are moving to the quantum bits, normally it is called as qubits. Okay, so first I will introduce about this qubits, and slowly we will see the difference between the classical computer and the quantum computer, why we are moving to quantum computers and qubits. Okay, so in quantum computers, for passing the information for operational purpose, we use qubits. Okay, why it is called qubits? It is called quantum bits. So here we are using zeros and ones. Okay, so here, okay, here we are using zeros and ones, but here you see we are having 3 states, right? 3 bits. Actually, these are not 3 bits. Actually, here also we are having zeros and ones, but this quantum computer will take all the possible states, including zeros and ones both. I will explain you later why it is zeros and ones. So this is called quantum bits. Because of that property called superposition, it takes both the bits, zeros and ones. So here the quantum computation and the quantum information is the information processing task in the mechanical system. Actually, if we want to clearly understand the quantum computing, first we have to understand the little bit of physics and mathematics, because they derive the quantum computing based on the quantum mechanics. So we need a strong mathematical foundation as well as the basics of quantum mechanics. Then we can easily come to know what is quantum computing. So actually, I will give a little bit of history and the introduction of quantum computers, and then we'll move to the basics of quantum computing. Actually, NASA is struggling of solving the research problem, scientific problem, challenging computational problems. So it is a time-consuming problem, or if it is a very complex scientific problem, they need more powers. So if you take classical computers, it is a time consuming process and it needs more energy. That's why the quantum computing comes into a picture. So we need a strong hardware platform, and then on top of it, we are using some kind of simulation tools and analytical tools, and we use the fundamentals of quantum mechanics. Then we develop quantum computing programming using Qiskit. IBM developed Qiskit. That is one kind of tool. And see that they develop Quniverse. So these are all the programming tools. And on top of it, quantum computing has several algorithms for, we can use those algorithms for many purposes. So we have search algorithms, we have teleportations algorithms, and we have optimization algorithms. Whatever you can do in classical computers, this quantum computer also support these type of tasks. So we have many algorithms. We can use those algorithms for developing such kind of problems, and we can bring some solutions. And then Feynman and Main recognized in the early 1980s. You think about 1980s. Now we are in 2025. So they use the quantum phenomena for simulation, and the phenomena, it is related to quantum entanglement. So I talked about this superposition, entanglement. I will tell you what is superposition and what is quantum entanglement. Without that, we cannot use quantum computation. So these are the main properties of quantum computation. Actually, you heard about the Charles Babbage. The first they introduced some engine. Now it is in museum. Actually, and later they bring all those computers in a smaller size, and we are start using the classical computers. Okay, so just because of using the quantum effects, we cannot say it is a quantum computer. We have to use some the properties. I told you, superposition, entanglement, interference. These are the important properties of quantum computing. If you use those properties for passing the information, for searching, for optimization, then only you can say these are all quantum computers. Actually, the general purpose, we need a quantum processors. So here in the first slide itself, I have shown the image, right? The quantum hardwares, how big it is, how complex it is. So we need the electron spins in silicon and atoms, and we have to use some topological structure. Then we have to construct the complex hardwares. Then the previous session also you heard about the the quantum hardwares. Then based on these quantum hardwares, now we are moving to quantum computation. Okay, so now I'll talk about these conventional computing versus quantum computing. Actually, the classical computers and the quantum computers. Actually, this conventional computing is purely based on the fourth generation of computers. Quantum computers are fifth generation of computers. Normally in quantum computing, we use the phenomena, right? So the phenomena of quantum mechanics, the superposition, entanglement. So why we are talking about this superposition? Normally, in classical computers, we use classical bits, right? So what are those bits? Zeros and ones. So if you toss a coin, either you take head or tail. Okay, so but in the quantum system or quantum computing, it will take all the possible states of those coins. Okay, so here if you take zeros and ones, it will take all possible combinations of zeros and one at the same time, simultaneously. This phenomena is called superposition. So why we are introducing this superposition? These are the quantum computing properties, superposition and entanglement. What do you mean by entanglement? Entanglement means if you take for example, layman point of view, I will tell you the example. If you have two gloves, okay, so left glove and the right glove. If you keep a right glove in one box and if you keep the right glove in the another box, okay, suppose you don't know which glove is in which box. So suppose if you find a right glove in one box, automatically you come to know the left glove is in another box. You need not to open that box. You automatically come to know, okay, left glove is that is in the closed box. So some combination, relation, correlation between these two. If you find a right glove, automatically the left glove is in the box. So this kind of relationship is there in between the quantum bits. Okay, so one bit is depend on another bit. Okay, if one qubit is in India, the another qubit is in America, there is some mathematical relations. This is called entanglement. This bit will depend on that bit. Okay, so this concept is called entanglement. So with the help of qubit, or we can call it as a quantum bit, we can store the information or we can do some manipulations in the quantum computers. So why we are talking about the quantum bits or qubits? These qubits are the basic building blocks of quantum computers. Whereas in the conventional computers, we use normally bits, zeros and ones. So if you want to pass information using the classical computers, normally we use zeros and ones. Okay. What are the basic building blocks of conventional computers? CMOS transistors are the basic building blocks. Whereas here, quantum transistors, qubit, superconducting quantum interference device, these are the basic building blocks of quantum computers. Why we are talking about quantum computers rather than the conventional computers? What conventional computers will do? Conventional computers store information inside the memory. They use algorithms, and for computations we use mathematical model, and will produce results based on the requirements or based on the task. Whereas in quantum computers, it is many times faster than the conventional computers as well as supercomputers. You please note this point. Quantum computers are as many times faster than the conventional computers as well as the supercomputers. So this quantum computing will be used in big data analysis and other forecasting, weather forecasting, climatic conditions, and for optimization or in searching techniques. In all those problems, if you give a task, so within a fraction of second or within the minimum time, we can get the results using this quantum computing. Okay, next important thing is how you calculate or how you imagine this quantum computing calculations. So if you have 10 qubit or to 100 qubit, so the 100 qubit quantum computer could perform over 1,000 billion simultaneous calculations. Why? Because how it is performed 1,000 billion simultaneous calculation? Because it has superposition and the entanglement. Superposition, so we can take all possible states simultaneously. That's why rather than classical computers, this quantum computers perform these many simultaneous calculations. Okay, now coming to the basic introduction of quantum. So far, we have seen the basic difference between the classical computers and the quantum computers. Next, the quantum mechanics. Normally, this quantum is based on the quantum mechanics. So this quantum mechanics uses this part and these calculations. Basic idea is quantum mechanics. Okay, so it refers to the properties of atomics. The basics of quantum computing comes from electrons, neutrons, and photons. Photons that generates the qubits. Okay, so in this quantum computing uses these quantum physics behavior to solve this complex problems, and it will do the massive performance. So here I talked about the specialized quantum property, superposition, entanglement, and the supportive algorithms. Actually, now only academic institutions are talking about this quantum computing and quantum mechanics. But the numerous labs, government agencies, universities, and other IT companies, they have developed this quantum computing technologies, and tech giants called Amazon, Google, IBM, they have developed this hardware system, and they started using the tools. Qiskit developed by IBM and CDAC developed Universe. So we can use those tools for developing or bringing the solutions for the major problems. And there's research universities, MIT, Harvard, and Oxford universities, they are using this quantum computings, and the National Institute of Standards and Technology are also using this quantum technologies. Next, coming to this introduction part of quantum computers, this quantum computing uses the particles. I talked about this electron. That is the basic things, electrons and photons, because the polarization, based on the polarization, we are bringing the qubits, right? So here, these units, the basic units are called qubits. So here we have the, actually, this qubits operation will be based on the superposition and entanglement. If you see this image, we have the difference between the classical and the quantum. This quantum computers have the superposition. So here we have either 0 or 1, 0 or 1, either this switch on or off, or head or tail. But if you take this qubits, so it is in the multiple states. Okay, so simultaneously it can perform multiple states, meaning all possible states simultaneously. Okay, so here entanglement, this entanglement is the qubits are depend on one another. Okay, so how it depend on one another? Actually, superposition, if it is in the suppose if you toss a coin, either it is in tail or head, normal in real-time scenario. But if it is in the superposition state, when you are rotating the coin, so if it is in the air, either you cannot say it is head or tail. Okay, so if it is in rotation, either you get tail or head, tail, head, tail, head. We don't know, either it may be 50-50 or 60-40 or 70-30. So this is called superposition state. So how will you know it is 50-50 or it is 60-40? That's why in the quantum circuit, at the end, we have to measure. So when you are measuring that state, you come to know whether it is in 50-50 state or 60-40 state or 70-30 or whatever may be the position. This is called probability distribution. So if it is, it may be either 60% of chance of getting 0 or 40% chance of getting 1. Here we can take 15% of chance of getting 0 or 80% chance of getting 1. So we come to know this probability because it is purely based on the probability. Normally, if you toss a coin, this probability is based on either you get tail or head. Okay. In quantum computing, this purely based on the probability distribution. So this qubits are depend on the quantum states. Okay. So either it is 0-0 or 0-1 or 1-0 or 1-1. This is probability distribution. So if you come to an entanglement, so here it depends, the quantum states purely depends on the number of qubits. For example, if you take 2 qubits, 2 power 2. So 4 states. If you take 3, 2 power 3, 8 states. So 2 power n. So the entanglement is the number of qubits. We are taking it for passing the information or for producing the solution. So it is depend on the number of qubits. The quantum states will be depend on the number of qubits. So if you take 3 qubits for processing 2 power 3, 8 states are there. So it is purely based on the wave function. So before moving to this Schrodinger equation, I will show this real-time waves. So as we are seeing water waves. So it is in the form of wave. And we heard sound waves and electronic waves, right? So waves on the string, the musical instrument. So how it is performed, how we are getting these waves. So based on this idea, so we are having this, if you toss a coin or if you pass a light, if you place a slit, it will be reached the other end based on the waves. So this quantum computing is purely based on the wave function. So here it depends on the Schrödinger equation. So this is represented as wave function. So this psi is represented as wave function. It is in the form of wave function. Okay. So, but we cannot see the waves, right? As you all know, we cannot see the waves. So we can either, we can see the waves, but we cannot see the quantum waves. Water waves we can see, but we cannot see the quantum waves. But we can measure it. That's why we can visualize them. How do you visualize? Based on the measurement, you can visualize this. Okay, so what is wave function? So wave function is purely depend on the time and the space. Schrödinger equation can be written as psi equal to a cos and that is minus AIC, because herely it is purely based on the linear algebra and the complex functions. So AI sine and then kx minus omega t. So it is purely based on the time and space. So it is purely based on the time and space, because what is K? K controls the size of the wavelength. Here we have the wave function. I told you, So if you want to measure the thing, because it is in superposition, when you are measuring that, then only you come to know how it is. So it is purely based on the measurement. So here what it is, K is the K controls the size of the wavelength, and it is omega. Omega controls the oscillation frequency, and this A controls the amplitude. So these are the properties or parameters of the wave function. So this is the explanation of this psi, A cos kx minus omega t, A minus AI sine kx minus omega t. So here these are the representation of the wave function. So here in the probability, actually I told you, this is the probability distribution, because we don't know which state it is in. When you are measuring, you come to know it is in this state. So because it has the property of superposition, so it will take all possible states simultaneously. Then how will you measure? So measurement can be done the modulation. So normally we'll take, we won't take the negative one. So we'll take psi mod square and psi into psi. This will use to represent the probability of the position. Okay, so the wave function can be measured by using the probability amplitude, probability of position, probability of momentum. Okay, so what are the constraints of measuring this wave function? So if you are measuring it, it should satisfy the Schrödinger equation. I told you about the Schrödinger equation, and the wave function should be like this, normalizable. And wave function should not be infinite area. Because if you talk about the probability distribution comes within the finite area. Then if it is a single wave, and it should be a continuous wave, it should not be a break in between, and continuous gradient. These are the constraints for the wave function. If it is there, then we will take that wave function. Otherwise, it will not be considered. Okay, so I talked about the superposition. So in the pictorial form, this is superposition. Assume that this is 0, assume that this is 1. So it is a combination of zeros and ones. It is covering all possible zeros and ones, states of zeros and ones. So this is the pictorial representation of superposition. For layman point of view, you can understand how the quantum property of superposition look like. Okay. And then superposition in another representation, wave function. If the cat is alive, we can represent like this. Another wave function, if the cat is died, we can represent like this. But in quantum computer, it is not like this. It is not 0, it is not 1. For example, if you take this is 1, this is 0, but in quantum computation, it is both. So we can take like this. We can consider both this and this, considering all possible combinations of the states, quantum states. Okay. Superposition, I explained with the picture, the layman point of view, and then I talked about entanglement. The basic, very classical example is that left and right glove. So I think you can understand the entanglement. This bit is depend on the other. Okay, so if we have 2 bits, 1 bit is depend on the other. So if we have 2 gloves, if you find a 1 glove, then other glove is in another box. You can easily find whether it is left or right. So this kind of relationship is called entanglement. Coming to the interference. Interference is the, actually this is called the blot sphere. Okay, so the qubit can be represented in terms of blot sphere. Really, it described, I told you, it is described in the form of quantum wave function, and the quantum wave function have the constructive and the destructive interference. Okay, so this constructive and destructive interference is used in this visualization of quantum computers. Okay, so if you have the wave function, if you combine these 2 wave functions, then you can get the overall wave function. This is called the interference. So the probability distribution of 3 qubits, 0, 0, 0, already you all know, 0, 0, 1, 0, 1, 0, and those things. So why I am taking this simple experiment, photon polarization, this is used to emit the qubits. So in CDAC, they have used this in dark room for generating the qubits. Okay, what is the use of polarization of a photon? Okay, that can be represented as a 2-dimensional vector of unit length. So here we have the horizontal and vertical polarization as a basis. Okay, so how will you represent this? Actually, this is the symbol, right? So this symbol, so here it is horizontal. This arrow represents horizontal, but here before and after arrow, we have the symbol. Here one straight line is there. Here one greater than symbol is there. This is called direct notation. The direct notation is used to represent the ket. So if it is a horizontal, you have to represent the horizontal using this, this representation. This is called ket direct notation. With the help of direct notation, we can use to represent the column and row vectors, because it is purely based on the linear algebra and vectors. Okay, so here it is used to represent the column vector and the row vector. So this is called ket and bra. Okay, so here it is normalized as mod A square plus mod B square equal to 1, because A and B are the complex numbers. Okay, so it is used to describe the circular polarization. As I told you, these are the direct notation for vectors. We have the column vectors and the row vectors, and ket and bra is used to represent the column as well as row vectors. This type of representation is called direct notation. Direct notation for representing the vectors. Okay, so I'll little bit talk about the linear algebra, as you all know, but this linear algebra and the quantum mechanics are the basis of quantum computers. Okay, so here if you take x square is equal to 4, x is equal to plus or minus 2. So if you take x square is equal to minus 4, then we use I. That's why we talk about the complex numbers that is used in quantum computation. So we call it as real number, imaginary numbers. This is the representation. These are the basic fundamentals of quantum computing. Okay, so before moving to the quantum computation, first you just brush up this linear algebra foundations, then you move to quantum computation, because the algorithm, the basics for quantum computing algorithms are these complex numbers, linear algebra, because we are using this plane. right? So we have two rotations. We have the gates and we have the rotations. So the vector rotations can be used using this complex numbers on the number plane. So you just to familiarize these linear algebra topic and then move to these things and a little bit of matrices, because the unitary operations will be used in the quantum computing. For unitary operations, we need to know unitary matrix, Hermitian matrix. I will little bit talk about this unitary matrix. So here the square matrix of complex numbers is said to be unitary matrix, that is equal, inverse is equal to the conjugate transpose. Okay. So if you have that, if it is a unitary matrix, if you take a conjugate transpose, that is equal to the inverse of the particular matrix. Or if you multiply the unitary matrix and the conjugate of this conjugate transpose of the unitary matrix multiplication, this multiplication is equal to the identity matrix. Okay. So unitary, what is unitary matrix? Actually, unitary matrix is a square matrix. It has the properties of orthogonal matrices. This is, I have given one example. So how to calculate this? This is the 2 cross 2 unitary matrix, and because it includes the complex numbers, this is the 3 cross 3 unitary matrix. So these are the, as you all know, these are the properties of unitary matrix. Unitary matrix should be a square matrix and non-singular matrix, diagonalizable, and two matrices are same order or added or subtracted. Okay. So here I have given the example. Prove that the matrix given below is unitary. So here they have given the matrix. We have to prove whether it is a unitary matrix. For that, what you have to do, you can take the conjugate matrix. Here I have taken the conjugate matrix. Then you multiply this unitary, this matrix, given matrix, and the conjugate matrix. So 1 by 2 into this unitary matrix into 1 by 2 into conjugate matrix. If you multiply this, you will get 1 by 4 into this calculation. 1 by 4, 4004. So if you simplify it, you will get 1001. What is this? This is the identity matrix. If you multiply the given matrix and the conjugate transpose of the matrix, then if it gives the identity matrix, then it is called unitary matrix. So these are the basic mathematics we should understand for understanding the quantum computers. These are the another examples I have given. And then stochastic matrix. Stochastic matrix is used in mathematics to describe the transition between the different states. Why we are talking about stochastic matrix? Because here superposition is there. So zeros and ones, it is changing the state from one state to another state. So we have to use the rows and columns, and we have to find the probability for everything. We have to use stochastic matrix. So these are the types of stochastic matrix, left, right, doubly stochastic matrix. If you add in this matrix, each column sums to 1 or each row sums to 1. So if you add each column sums to 1, then that is left stochastic matrix. If you add each row, then the matrix sums to 1, then that is called right stochastic matrix. And this is doubly stochastic matrix, both row and column. Okay, so I talked about the basics of quantum, that is mathematical foundations, linear algebra, maths, everything. Okay, then we'll come to the vectors. I talked about the vectors, right? So here vectors are represented using the direct notation, because this is the notation. That notation is used to represent the row vector and the column vector. Already you have gone through the row vector and column vector, but these vectors live in some space, right? Normally vectors live in some plane, right? So here these vectors live in some space. That space is called Hilbert space. That space is called Hilbert space. Okay. So here the elements are called kets. I talked about the direct notations, right? So here the basis vectors, 2D Hilbert space, okay? So row and column. So here it is called ket0. This is called ket1. Okay, if it is a column vector, it is ket0 and ket1. If it is row, bra0, bra1. Okay. So now, if you combine both row vector and column vector, this is called bracket. Bracket, row and column. Okay. So a ket for a single qubit can be represented like this. Ket0 and ket1, these are the computational basis vectors, right? You can see this diagram. By convention, these can be represented using the kets. And then if you, here it is probability, purely based on the probability, right? Either we'll get 0 or 1, true or false, or tail or head. So we need some complex numbers. So alpha and beta are the probability amplitudes. Okay. So this will be represented using the 3D visualization that is called blot sphere. This is called the blot sphere. Okay. So here the row and column, row vector and the column vector, here row vector and the column vector, these are perpendicular to each other. So R vector, S vector, row vector and column vector form, or horizontal and vector form an orthogonal basis. Okay. So this is the representation in the these are the basic idea of learning quantum computers. That's why I am touching all these linear algebra, vectors, because we are using the vectors here. The vectors live in n-dimensional vector space that is called Hilbert space. That is called Hilbert space. These are the abstract vectors, and we can do products, right? If we have a vectors, we can multiply using dot products. Okay. So this is called inner product. Okay. So we use polynomial functions for finding some values. So here we have the rotations. So we need to know how it is rotating. We have some gates. So that's why we have to go through all these polynomials and other things. So if it is polynomial, so then the Hilbert space, the vector space, that is, if you say it is complete, then it is a polynomial and has the inner product. That vector space plus inner product, then only we can say it is complete. So I have given some examples. Okay. So these are the basic gates of quantum computing. So here we have different gates. First gate is identity gates. So the representation, first you will see the matrix representation. This is familiar for you, but then we'll move to the computational basis. So what is computational basis? I told you. So ket0, ket1 for representing the column, and bra0, bra1 and for representing the row vectors, row bits. Okay. So this is the, as you all know, this is the identity matrix. Okay. So here this is ket0. How to pronounce this? Ket0. Okay. This is ket0, ket1. And this is poly X gate. This poly X is the matrix representation of poly X because these are the gates we use in quantum computers. So poly X gate, poly Y gate, poly Z gate, and phase. So this poly X gate is called bit flip. Okay. So here we are using only bits. The bits are flipped. Okay, so it is changed from 0 to 1 or 1 to 0. That's why it is called poly X gate. And if you have the phase, the rotational angle basis, then it is called poly Z gate 0, 1, 0, 0, minus 1. Because if you rotate, you will get the negative value also. So phase yes, and T gate and Hadamard gate. So here this is Hadamard gate is very, very important. Why? Because if you, when you are constructing a quantum circuit, the inputs may be the qubits, right? 0 and 1s. So if you want to introduce the superposition in that, then you have to use Hadamard gate, because Hadamard gate will bring the superposition in the quantum circuit. So this is the input. This get 0 is the input. When you apply Hadamard gate on the input get 0, then you will have this computational basis 1 by root 2 of get 0 plus get 1. And if your input is 1, get 1, and if you use the Hadamard gate on it, then you will get the get 0 minus get 1, 1 by root 2 of get 0 minus get 1. Okay, so if you are writing the matrix representation for get 0 and get 1, this is the representation 1 by root 2 of 1, 1, 1 minus 1. So here I have given the computational basis states and the matrix representation of all these gates. Okay, so this Hadamard gate is important because that brings the superposition. Then you can ask me what is tensor product. Okay, so tensor product, and so here it is get psi because it is in the direct notation. So A and it is get 0 plus B get 1. Okay, so if you are writing the quantum states like this, then it is in the direct notation. Okay, this is the representation of quantum state in the 2D basis. Okay. So here basis states are represented in the direct notations. So here if we have a die, okay, so 6 positions are there, get 1, get 2. So if you take a coin, you have 2 positions, 2 states. Get 2 states are tail and head. So or you can have a 0 or 1. So how will you represent it? Get 0, get 1. So if you take a die, you have 6 states. So how will you represent it? Get 1, get 2, get 3, get 4, get 5, get 6, and so on. Okay, so coming to the tensor product, if we are having 2 vectors, okay, so this it has the product, Cartesian product of these 2 vectors is called tensor product. Okay. So here we have 2 things. If we are having these vectors, then if you do the multiplication of these 2 vectors, this is called tensor product. Okay, or it is called Kronecker product of 2 vectors. So why tensor product are necessary? Because we are using these states and superpositions, and we have some calculations. So if we are having this row vector and the column vector, if you multiply these 2 things, then only you can get the superposition states, right? So far we talked about the basics of quantum computing. If you want to really know about the quantum computation, you should understand how the linear algebra is used in this quantum computing. So you just recall linear algebra, vectors, probability, all those things. Okay, so quantum gates. So using the quantum gates, now then we will construct the quantum circuit. Okay, so these are all this poly X, poly Y, poly Z or single qubit gates. Right. So here we have the elementary computation. If we have the qubit, so it will be, for example, if it is 0, then it is 1. The transition will be there. Okay. So this is the basic thing. I told you about the direct notation, right? So in mathematics, it is vector form, and here it is direct notation get. Or if you want to do the matrix multiplication, you can do the matrix multiplication. So these are the poly X, Y, Z gate. So this is the poly X gate. This is the representation. So Q represent the qubits. So here it is the X gate. So how it performs, this is the matrix of poly X gate. Okay, you will get this result because column vector is represented as get 0 and row is represented as get 1. So column vector, row vector, column vector, row vector. So this is the output of this poly X gate. So if you give a input of 0, so what is the matrix form of 0? 0 is 1, 0. So here poly X is the matrix representation is 0, 1, 1, 0. So if you want to give this get 0 as an input for poly X gate, so this is the matrix form of poly X gate. 0, 1, 1, 0. And what is this 0? This get 0. If you multiply, finally you will get 0, 1. What is 0, 1? 0, 1 is the matrix form of get 1. 1, 0 is the matrix form of get 0 and 0, 1 is the matrix form of get 1. So finally you will get 1. So what you will understand from poly X gate? Poly X gate will change the bit from 0 to 1. Can you understand now? So this is the qubit. This is the poly X gate. I am giving this input. This is the poly X gate matrix. So what is the matrix representation of get 0? 1, 0. If you multiply with this, you will get 0, 1. What is 0, 1? This is 1. So poly X gate will change from 0 to 1. This is called bit flip. Bit flip means what? So the bit 0 is changed to 1. Get 0. Because in quantum computers, the direct notation is used. So the representation is get 0, get 1. Okay. So here I am doing this multiplication. So here I am giving all the three gates, poly X, poly Y and poly Z gate. This is the representation. Just for circuit purpose, you give like this X, Y, Z. So the matrix form of poly X gate 0, 1 and 1, 0. And poly Z gate is 1, 0, 0 minus 1. Poly Y gate is 0 minus I and I is 0. So if you give input 0, then you have to multiply with this matrix and you will get this. And if you get give some 0 or 1, then you will get some sort of answers. Bit flip and phase flip. Then Hadamard gate. So what is the purpose of Hadamard gate? I told you Hadamard gate will bring you the superposition in the qubits. So here this is the quantum bits. This is the basic circuit. If you use Qiskit, you can find this circuit. So here that is the open access. You can install and you can use the Qiskit. Many tutorials are available. So this is the matrix representation of Hadamard gate. Hadamard gate will bring you superposition. So 1 by root 2 of 1, 1, 1 minus 1. So you can give the inputs and multiply it and then you will see the results. So it will bring you the superposition 0, 1, 1, 0, everything. And then we have the S gate, swap gate. So swap will change the plus into minus and minus into 1 and also the phases. So these are the basic building blocks of for constructing the quantum circuits. Okay, so we can simultaneously or we can use this poly X gate, then get the result and apply Hadamard. What you will get? So first you are giving 0. So if you use poly X gate, then it will be changed to 1 because poly X gate will change 0 to 1, 1 to 0, bit flip. And if you apply Hadamard gate, then the superposition will be applied. These are the simple calculation I have given here. Why I talked about the unitary matrix? Because this is purely based on the unitary matrix. Then this is the sample, quantum circuit sample. I told you, it is taking some superposition, right? So if it is in the superposition, then we cannot identify the state of the coin or dice. Okay. So finally, how will you identify whether it is in this state or that state? So for that, you have to observe. Observe means here we have to measure. So this symbol is used to represent the measurement. Okay. So this is the computation. This is the input. Okay. So this is the qubit, either 0 or 1. Poly X gate is applied here. And after that, Hadamard for getting the superposition. Okay. So here C represents the classical line. This is quantum line. This is the classical line. So finally, you get the output and we can represent the output in terms of classical bits. That's why these two lines represents the classical line. Okay. So if you measure this Q dash, what is Q dash? I am taking the qubits, I am applying the poly X. Poly X is sigma X. And then I am applying Hadamard. If you are constructing a quantum circuit from left to right, actually in the equation, we have to read from right to left. This is the qubits, Q, representation Q, this one. And this is the poly X. This is the poly X bit flip. and this is the Hadamard. Okay. Then if I substitute all these values here, I will get the result. Okay. So don't forget, this is the classical bit. After measuring, you have to read the values in the classical bits. So previously I have shown a single bit case. Okay, single qubit. Okay, this is for 2 qubit states, Q1 and Q2. What is this? This is the tensor product. If you multiply these 2 qubits and you have to do the tensor product, this can be represented. If you have n bits, then we can represent 2 power n states. Here we have 2 qubits, so 2 power 2. So how many options you will get? 4 options you will get. That is the basic. Okay, if you have, because I told you, no, entanglement, the quantum states will depend on the qubits, right? So here the number of qubits. So here we have 2 qubit states. So this will multiply this qubit and this qubit tensor product. You will get 4 states. Okay, so here it is the direct notation 0, 1, and you have to give the this is the input and do the tensor product. 0, the matrix form is 1, 0 and 1, 0, 1. And then if you multiply, then you will get 0, 1, 0, 0, and then you will get the results. This is the representation. Four possible outcomes, because 2 qubit states. How will you get 4 possible states? Because if you have n number of qubits, we can represent this n qubits in the form of states, 2 power n states. You will get 2 power n states. So you will get Q11, Q21 of 0, 0, Q11, Q22 of 0, 1, Q12, Q21 of 1, 0, and finally you will get Q12, Q22 of 1. So these are the 4 possible outcomes. Here I explained the single qubit with the poly X gate and Hadamard gate, and finally you can measure, and final outcome, it is representation in classical bits, and this is Q qubit states, 2 qubit states. So you have to use the tensor product, the direct notation, everything. This is for n-dimensional vector. Suppose if I'm using n-dimensional, so 2 power n-dimensional vector, multipartite state, so Q1, Q2, Q3, Q4, and go on up to Qn. So you can also have this matrix, then you have to multiply. If you take it, this is in the normal qubits notation. This is if you take it in the direct notation, 0 to the power n. So if I want to represent to the power n, then you have to give the tensor product to the power n like this. This is the to the power n and zeros, and you can have as many zeros, n number of zeros, and 0, what is the matrix form? 1, 0. And if you are having, suppose 1, the matrix form is 0, 1. So you can multiply with the tensor product. Finally, you will get like this. So this is for n qubits and the representation 2 power n. And the state classification. So here we have the product states. So if you have 0, get 1. If you do the tensor product, so how will you get this one? So 1 by 2 of 0, 0, 0, 1, all these things. So finally you will get 1 by root 2 of get 0, 0 plus get 1, 1. So this is called this actually the entangled state. This will be depend on the another state. Actually, we have the n number of algorithms. One kind of Dutch-Joshua algorithm. So this Dutch-Joshua algorithm is mainly for speeding up the algorithm, speed up the computational. So you have the classical algorithms, right? Sometimes if you have a complex problem or very scientific, complex scientific problems, it will take more time. So I want to reduce the time. I want to minimize the resource utilization. Then I can go for this quantum computing Dutch-Joshua algorithm. This will speed up the computation, because how it speed up the computation, because in classical algorithm, for getting the solution, it will take more number of time, iterations, doing the calculations. So it will take more time to process. But here, if you do 10 times, here you can do 2 times. That is the main idea for layman point of view. So if you do 2 times there, you can do 1 time. If you do 4 times there, you can do 2 times. That's why you can reduce the time and minimize the resource utilization. So you can, if you want to save the time, you can go for Dutch-Joshua algorithm. Okay. So Dutch-Joshua algorithm actually has 5-step process. Okay. So here we have the, actually I talked about the quantum gates and the circuit, how to construct the circuits. So we have the line, quantum line, and if you insert, then you have to give the input. The input will be stored in the registers, and then you have to introduce or include the quantum gates, whether poly X gate or Y gate or Z gate, depends on the process. Then you include the Hadamard for bringing the superposition. Finally, at the end, you can measure. Then finally, you can give the representation in the classical bits. So here in Dutch-Joshua algorithm, we need 5 steps. So first, quantum registers and the input states are prepared, because we need quantum registers for storing the quantum bits and input states. So gate 0, gate 1 and other gates should be included. In the second step, qubits are organized and into the Hadamard basis. Why we need a Hadamard basis? Because this Hadamard basis will bring you the superposition. Normally talking, we get a 50% chance of being 1 or 0, or 80-20 or 70-30. But whatever may be, we need to include the Hadamard gate. That is the second step. Third step is the oracle. That oracle is the actual function. This Dutch-Joshua algorithm is also called as black box algorithm. Why? Because this oracle is a black box. Some functions will be done, but it is not explicitly known to the user or the developer. So that's why it is called black box function or black box algorithm. So this is the oracle function. We use the oracle function, which encodes a function that will determine if the outputs are either constant or balanced. Okay. So fourth step returns the qubits to the measurement basis. Fourth step, actually in the previous circuit, we have seen the measurement, right? So finally, if you want to know the results and know the states, we have to get the measurement. So we have to use this measurement. And finally, based on the measurement, you can obtain that is the representation in the classical bits. That is the solution. So this is the Dutch-Joshua algorithm. Actually, here I told you about the oracle function, right? That's why they have given hidden Boolean function. That oracle function is represented as F. Okay, so that will take the input string of bits. Okay, so string of bits can be represented. We don't know how many zeros and ones are there. So 0, 1. Zeros and ones are there to the power n. So string of bits are there. So we can take the output. So here here we are using the hidden Boolean function in Oracle that will give you either be balanced or constant. Okay. So it is constant. It will return either all zeros or all ones for the given input. So that is called constant function. Okay, you can get either zeros or either all ones or all zeros. That is called as constant function. Otherwise, the zeros and ones balanced combination, 0, 1, 0, 1, like that, then that is called a balance function. Half of the output are zeros and half of the outputs are ones. Okay, so for example, if your function is 0, 1, 1, 0, then if you get the output as 4 ones or 0 or 4 zeros, then it is constant. whatever may be the input, the function, the hidden Boolean function that is called oracle function, that is applied on this input, you will get the constant. Okay, so here that is the representation, that is the final thing. Then we have to use the measurement and get the output in the classical form, because we should understand the measurement, right? So we have to take it in the classical form. Then you use the function 0 for 2 inputs and 1 for other 2 inputs. Then that is called balance. So this hidden Boolean function will give you either constant or balanced. Okay, so here minimum of 2 and a maximum of 2 power n minus 1 plus queries. So we'll get the probability in the thing. So the result may be either 0 or 1. If you get all zeros or all ones, then that is constant. And then if it is 0 and 1 combination, then it is balanced. So this is called the quantum circuit. Actually, previously you have seen the quantum circuit, single line is there, right? So I have given Q. Q is the qubits. That is a single line, and we include the poly X gate or Y gate, whatever may be the gate. And then we include the apply Hadamard gate, and finally we measure and we'll take the output. That is the basic thing. But Dutch-Joshua algorithm quantum circuit is like this. Okay, so here we have the input. So input is a strings, right? So here in this line, we are taking the strings of 0. Why we are giving n number of zeros? Okay, that's why this line is taking n number of inputs. Okay, so this is n zeros are going. This representation is showing zeros are going. And in this line, we are giving the input 1, ket 1. We call it as ket 1. Normally, we have to tell ket 1, ket 0. Okay. So then we apply Hadamard for the n inputs. That's why I am giving Hadamard to the power n. Because here n number of zeros are there. But here it is not like that. Only one input, ket 1. That's why here I am not giving these to the power n. So here they represent the Hadamard, here Hadamard to the power n. And then finally here we are, this line represents the, showing the output, intermediate output of this one. Okay, this is called oracle. I talked about the hidden Boolean function, right? So this input is called X, this input is called Y, and this is applied on this hidden Boolean function. This is called oracle. So whatever input you are giving here, you will be getting the same. So this X is getting here. But in this Y, you will be getting Y tensor product, okay, f of X. Okay, so some function will be applied in this oracle. Okay, so here I have given this. So first I will explain this circuit, then I will move to the calculation part. Y tensor product f of X. This f of X is the oracle function. Okay, why they are giving U? Because I talked about unitary transformation. Here all the operations are unitary transformation operations. The base for unitary transformation operations is unitary matrix, Hermitian matrix. That's why in the beginning I talked about linear algebra, matrix, everything. Because when you want to understand this function, if you expand this function, you will come to know the mathematics are included here. So here it is X. So then we have to apply this Hadamard. Then the second, this here we are taking some intermediate output. Then we apply Hadamard, and then we are taking the measurement. Here the output is going like this. If it is this, then it is represented as identity matrix. If it is single line is there, plain line is there, then it is identity matrix. Okay, come to the calculation part. This is the input, this is the target line or ancilla line. So here this representation, computational basis state. So ket psi 0, so strings zeros to the power n, and here it is 1. So when I am measuring, not measuring, actually this is the measuring. When I take the output of this one, this is the thing. Okay, so this get psi 0 gives you the intermediate results of this one. So what you are getting, just we are getting these strings, input strings, zeros to the power n and just 1. So this is the combination here. And when I am getting the intermediate output, this line, I am taking this representation is get psi 1. This is actually 1. 0th output, 1th output, second, third, right? So here it is ket psi 1. So ket psi 1 is the 1 by root 2 of n, because here we are applying what? Hadamard gate. What is the formula for Hadamard gate? 1 by root 2 of this ket 0 plus ket 1 square root of 2. So when you are applying this 1, then it is, when you are applying ket 1 to Hadamard, then 1 by root 2 of ket 0 minus 1. So if it is input 1, it is plus. So why we are taking this summation? Because here we are having zeros and ones to the power n, strings. Okay, so this is the output x with the Hadamard. Okay, so summation is for n number of strings. Okay, and then Hadamard 0. Okay, so first here they have given with a single bit, and then they are increasing the number of bits with 2 bits, then they explain with n bits. Then only we can easily understand how the input 0 is applied, how the Hadamard gate is applied on the input ket 0. This is qubit, right? Ket 0. Normally, this qubit is slowly, we are representing it as ket 0. So this ket 0 is the input. We apply Hadamard. Actually, this is the state. But here, this is n numbers. But for understanding, we are taking a single bit. Okay. So 1 by root 2. What is ket 0? If you apply Hadamard on it, 1 by root 2 of ket 0 plus ket 1. That is Hadamard. Hadamard representation is this one. So if you have the Hadamard for the input 1, 1 by root 2 of ket 0 minus ket 1. So if it is 1, it is minus. If it is 0, it is plus. Okay. So this is Hadamard for a single input, single qubit. So if I take 2, so Hadamard to the power 2 and ket 0 to the power 2. What you have to do? So you can take this Hadamard value and ket 0 value and then multiply it. So if you multiply 1 by root 2, 1 by root 2 becomes 1 by 2, ket 0 plus ket 1 and ket 0 plus ket 1, both the things, right? So if you multiply these two, 1 by 2, 0, 0, 0, 1, 1, 0, 1, 1. Normal thing. If you add these things, then 1 by root 2, zeros and ones to the power 2. Why? Because I am taking, instead of n, I am taking 2 bits. So 0 and 1 strings to the power 2. This is represented as this. Okay. So if you take n, you will get this strings in n combinations, right? So finally, I can write ket x. The representation of ket 0, 0, 0, 1, 1, 0, 1, 1 can be represented as ket x. Okay. So for understanding, I am just displaying this circuit again. So this is psi 1, psi 2. So here, so we finished this 1 and 0 and 1 intermediate output and applying quantum oracle. So here we have ket x and ket y, and we are getting ket x and y tensor product. That is also ket y tensor product f of x, right? So this ket x applied on this 0 ket 0 with f of x minus 1 into f of x. So here we multiply. So ket x f of x minus, if you multiply with 0, you will get x with the f of x minus 1 with the tensor product f of x. If you do a normal thing, you will come to know. Then this part, psi 2. Psi 1 is over psi 2. Psi 2 is the strings to the power n. 1 by root 2 to 1 by root 2 to the power n sigma, because we are taking n number of strings here. So 0, because x belongs to 0 and 1, but input strings, series of strings, 0, 1 to the power n. So get psi, then you have the calculation here divided by root 2. So if f of x is equal to 0, this one, then you will get this result. If f of x is equal to 1, because we don't know whether it is 0 or 1. So if it is 0, you will get this one. If it is 1, if you do this calculation, you will come to know, because here I didn't put the intermediate calculations. So you will get these values. So this is about Dutch-Joshua algorithm. And then we have Groover's algorithm. I didn't include here, but I will talk about this Groover's algorithm. Normally, you heard about the search algorithms. Normally, breadth first search, depth first search. Suppose if you are having 100 elements, if you want to find out the 90th element, so you have to search first 10 elements. Okay, 90 is not there. Second 10 elements, 90 is not there. Then next third 10 elements, 90 is not there. So finally in the the ninth row, you will find the 90th element. So you have to follow some strategy, either BFS or DFS or binary, whatever may be. We study a lot of algorithms in various subjects. But in quantum computing, we have Groover's algorithm. Okay, so in Groover's algorithm, it has the qubits, and I talked about this Dutch-Joshua algorithm. If you want to do a calculation 4 times to get the result in normal classical algorithm, here you can do only 1 time to get the solution, to save the time, to save and minimize the resources. Like that, you can search it easily, and you can minimize the number of iterations to get the results. That is called Groover's algorithms. And we have QAOA or optimization algorithm to suppose if you want to find the shortest path from source to destination. Already you have studied the Dijkstra algorithms and so on. Many path algorithms, optimization algorithms are there. But in quantum algorithms, we have the optimization algorithms. You can take the output and will give it to the QAOA, and it will be optimized, and it will reduce the time also. So you can minimize the resources. So many algorithms are there. So if you first go through all the basic mathematics and physics, then if understand these gates. So I talked about these gates, right? So understand these gates and these block sphere, understand the rotations. When you are rotating the spin, you will get some rotations, right? 90 degree, 180 degree. So you will get the rotations, because here why we talked about these rotations, because it introduces superpositions, entanglement. So once you understand this basics, easily you can understand the algorithms. If you have any doubt, you can ask me. If you have any doubt, you can ask me.
A nice presentation, ma'am. I have one question.
Yes, sir.
So regarding arbitrary single qubit state, so we use Solvay-Kitov theorem for that.
Yes, sir.
But you are observing on quadruple states like 0, 0, 0, 1, 1, 0, 1, 1. That theorem is not valid. Is there any validation scheme regarding that, ma'am?
Which one, sir? For which one validation?
For quadruple states, like a single qubit state and the double qubit state and triple qubit state, Solvay-Kitov theorem is working. But if you are considering 4 qubit states, then this theorem is not valid. That is a bottleneck observed recently by IBM also. So is there any validation mechanism that we can that is there in pipeline for consideration?
For multi-qubit states, sir?
Yes, ma'am.
Actually, in CDAC also, they are trying to resolve it. Okay. So, as you said, they are doing the research, sir.
Okay,
But if you
okay.
take more number of bits, it is in the research problem, sir.
Yes. Thank you, ma'am.
Thank you, sir. Actually, I wanted to tell you some of the problem statements that will be useful for doing the research work. Wait a minute, I will share. Actually, if you want to do a simple project, you can give the problem statement like generate random bits using quantum random number. Please note down. I didn't include it in the slide. I will tell you. The problem statement is quantum random number generator. So you can QRNG. You can use this QRNG in the design basic QRNG in the quantum circuit that utilizes the superposition. So you can measure and you can generate the random bits. In cryptography, you have to use the random bits, right? So for security purpose, so you can use this as a small project. And another second problem statement is design a basic simulator using quantum key distribution protocol, actually QKD. In cryptography, you all know we want to distribute the key from sender to receiver. We have Alice and Bob. Alice and Bob want to do a secure communication, right? So if you want to do a secure communication either in symmetric or asymmetric way, and if it is in the symmetric way, they have to share the key. In quantum also, we have certain protocols, BB84 protocol. Please note down. BB84 protocol that is used to do a secure communication in using the quantum principles. Okay, so you can use BB84. You can include this BB84 protocol for QKD problem. Then third problem statement is you can ask the students to develop a tool or maybe an app that accepts multi or 2-qubit quantum circuits that isolates the single qubit, reduce the density matrices. So here it is for Blot sphere rotations. You can give it as a thing. And then one more concept is there, quantum teleportation. That is also an important concept in quantum computing. Quantum teleportation, actually, I will tell you the scenario. We have Alice and Bob, sender and receiver. Assume sender and receiver. We have Alice and Bob. So suppose I am the Alice, you are the Bob. I want to share some information in a secure way. This quantum teleportation provides a secure platform to teleporting. Teleporting in the sense, whatever information Alice is passing, the Bob will receive the same information. But this cannot be cloned. So we can avoid the intermediate user or the eavesdropper. So it cannot be cloned, whereas you can the information quantum bit is passed. Okay, so for that we can use quantum teleportation. means the information is passed from Alice to Bob without doing any cloning. That is called no cloning theorem. It is important concept in quantum computing. You can ask the students to implement quantum teleportation. Circuit is readily available. You just take the circuit and use Qiskit, that is open source, and you can implement and you can see whatever the information Alice is passing, whether the Bob is getting or not. And we have one more algorithm in drug discovery and estimation. So for estimating this molecule energy estimator can be used here. Or our students are doing project using this optimization for one place to another place. You can use optimization algorithm, and for forecasting the weather. And one more project is about customer churn prediction project is there. Normally, if you are using Geo or Airtel or whatever may be the network connection, sometimes if it is not okay for us, we will move from one network to another network. If you are using Geo, if it is not good in your area, you'll be moving to Airtel or some other thing. So they have to predict the customer churn, right? How many users are moving from our network to another network. So if the company is predicting that one, then only they can take action on their side to give the solution, right? So that kind of problem statement can be given. And fraud detection during transaction, or the Facebook or any other profile fraud detection can be done. And logistics. So if you want to move from one place to another, for example, now we are using Google Map to find the destination, right? So sometimes it will not give you the right path. So it will give you, guide you to the narrow road. If you are traveling in the four-wheeler, it's very difficult to take up the road and reach the destination. So for that, we can use this path optimization algorithm. So many problems are there using, but they are very simple. Once you go through the circuit, you can easily use Qiskit. Then you can understand the results, get the results.
Thank you, ma'am.
Thank you, sir. Thank you, sir.
Participants, if you have any queries. Participants, having any queries, just raise your queries for 3 minutes.
Yes, I will share my presentation to Chandrakant sir.
Madam, thank you. Thank you very much.
Thank you, sir. Thank you,
Today
sir.
we have a wonderful session, madam.
Thank you, sir.
Great
Thank you so
session,
much.
madam. We are getting very well feedback from this session recording, madam. We are receiving madam, from the participants.
Thank you, sir. Thanks a lot.
Madam, 1 minute, madam. Madam, thank you for giving your valuable time and wonderful deliverables on our respected ATAL-sponsored one-week faculty development program on quantum cryptography-enabled autonomous underwater vehicles. Madam. We are very much thankful for your kind participation, madam. For your kind participation. Harivom, madam.
Thank you, sir. Thank you, sir.
Harivom, madam.
Thank you so much.
Ma,
Thank you,
Ritika?
sir. Thanks for the opportunity, sir.
We are
Thank you,
very
sir.
much beloved, madam, for your
Thank you.
sincere efforts for delivering a wonderful deliverables on our respected online one-week faculty development program towards the quantum computing, madam. Thank you, madam.
Thank you, sir. Thank you.
Thank you, madam.
Thank
Ma,
you for
Ritika?
all the participants.
Ritika? Madam, 1 minute, madam.
Yes, sir.
Yeah. Proceed, ma. You can proceed, ma.
Yes,
Ritika.
sir. Dr.S. Bhagavathi Priya ma'am, thank you so much for sharing your valuable insights and expertise with us today, ma'am. Your dedication to teaching and research is truly inspiring, and we gratefully honor you for the knowledge you have shared with us. Your contributions to the field of computer science and engineering are commendable, and we appreciate the time you took to prepare and present your session, ma'am. Once again, thank you so much, ma'am, for your presence and valuable inputs. We hope to benefit from your expertise in the future too, ma'am.
Thank you, madam.
Thanks for the opportunities. Thank you, sir.
Madam. Regarding our participants, kindly share your respected PowerPoint presentations, madam.
Sure, sir. Sure.
Sure, madam. Thank you, madam. Thank you, Harivom, madam. Harivom, madam. Dear participants, by next session 6, Kartick Sutradhar sir from IIIT-SriCity is ready to join. Please take a break for 5 minutes. Dear participants, from IIIT-SriCity, Dr. Kartick Sutradhar sir has been already joined. You can take a break for 5 minutes. Exactly 7:35 again, the session is going to be started. Dear participants, kindly take this updated feedback link and you can give your valuable feedback by using this updated feedback link. Yes, we are sending, sir. We are sending. Kartick Sutradhar sir already joined. Dear participants, kindly join the session. Exactly 7:35, the session is going to be started. Sir, very good evening, sir. Kartick sir. Very good evening,
Yes,
sir.
sir. Good evening, sir.
Very good evening, sir. Harivom, sir.
Good evening. Harivom.
Thanking you for joining for our ATAL-sponsored one-week faculty development program on quantum cryptography-enabled autonomous underwater vehicles.
Thank you so much, sir.
Thank you, sir. Thank you, sir. Sir, give me 3 minutes of time, sir. Just now only the session is winding up.
Okay, sir.
We are giving the break for 5 minutes of our participants. 7:35 sharply, we are going to start the session, sir.
Okay, sir. No problem.
Thanking you for your valuable presence, sir. Thanking you for your valuable presence. Thank you.
Thank you so much, sir. So, sir, can I share my PPT? Okay, once you just check it is visible or not properly. Or
Yeah, sure, sir. Sure, sir.
Okay, so I am sharing my PPT.
Sure, sir. Sure.
So, is it visible to you?
Yeah.
Visible, sir.
Okay, fine.
Yeah, visible, sir.
And
Visible.
if I'll keep it like that, is it okay, or should I do it full
No,
screen?
no. It is okay, sir. It is good.
It is okay, correct? If
Yes,
it is,
sir. It is okay, sir.
same you are getting.
Yeah, yes, per.
Okay.
Right.
And one more thing, if I'm writing something, is it visible to you or not?
Yes, sir. Visible, sir. Yes, it is visible, sir. It is visible, sir. If there is a chance, we can maximize, sir. If there is a chance, we can maximize.
Okay, because it's required for me. Okay, so
Yeah.
I'm going to discuss little bit, basic themes. Okay.
Yes, sir.
So that it will be very helpful for the student, because you know that as that national quantum mission is going on. So if some of the students of ours is going to contribute for our country, so it will be very helpful for them. Okay.
Yes.
So they may later on go for higher studies, they may go for research. Okay, even some of the faculties also joined here, correct?
Yes, sir. Participants has been participated, those who are working as a faculty members in different states and different universities. Those research scholars also has been joined in our ATAL sponsored 1 week faculty development program. Those who are pursuing their valuable PhD degree in most reputed universities. Those also we are having participants. Those also
And title page is fine, sir.
Yes, sir.
Basically, I have not got very more information, so I kept your institute logo as well as auto logo.
Yes, sir. Yes, sir.
So I think Odilo sir already presented, correct?
Yes, sir. Yes, sir. Already presented, sir. For their freeness, we are giving only 5 minutes of time, sir. Exactly 7:30, the session is going to be winded up, sir.
Okay.
That session 5 forward 6. Yes. Ma Ritika. Ritika.
Yes, sir.
Yeah,
Yes, sir.
yeah. 1 minute, ma. Next you can take the
Okay,
session.
sir.
Sir, shall we start the session, sir?
Yes, we can
With your
start.
permission.
Yes, we can start.
Yes, dear participants, kindly join the session. The session is going to be start. This session is going to be handled our respected eminent resource person from IIIT-SriCity, who is working as a associate professor from the Department of Computer Science and Engineering. He is Dr. Kartick Sutradhar, sir. Ma, Ritika, kindly introduce the Sutradhar, sir. No?
Yes, sir. Respected guests, esteemed faculty members, and dear participants, it is my privilege to introduce our distinguished resource person for today's session, Dr. Kartick Sutradhar, sir, Associate Professor in the Department of Computer Science and Engineering at the Indian Institute of Information Technology, SriCity, Chittoor, Andhra Pradesh. Dr. Kartick, sir, has completed his PhD in Computer Science and Engineering from the prestigious Indian Institute of Technology, Dhanbad, MTech in Information Technology from National Institute of Technology, Durgapur, and BE in Information Technology from the University of Burdwan. Sir, your research areas include quantum computing and cryptography, and sir has also published numerous papers in esteemed SCI or SCIE index journals, including IEEE Transaction. You have also filed a patent for method and system for secure multi-party quantum aggregation, sir, which showcases your innovative approach. We are honored to have you share your expertise with us today, sir. Your presence is a testament to your dedication in the field. So we heartily welcome Dr. Kartick Sutradhar, sir, with a warm applause.
Thank you, ma Ritika.
Thank you, Ritika, for introducing me. Okay. I'm going to start this session. Okay, so this my topic is basically importance of quantum entanglement and superposition in quantum cryptography. Okay, so before going to my presentation, I want to give you some basic concept of quantum cryptography, quantum computing. Okay, why we need it, why we require it, why we have already supercomputer or very high performance computer already we have. So why we require this quantum computer now. Okay, so this is basically outline of presentation. Okay, so first I will discuss some basic things about cryptographies, quantum computings, then quantum cryptographies and all, and then I'll discuss about one of my research which is published in IIIT Transaction on intelligent transportation. So there how I designed a protocol. So all those things I'll discuss in this presentation. Okay. So first thing is like that, what is quantum computing? Okay. So it's basically quantum computing is a computing which is basically following the quantum mechanics such as superposition, entanglement, and which can compute any functions or execute any protocols faster than the classical computer. So next is superposition. So what is called superposition? So superposition is a mechanism. As we know that our classical computer has two only states. One is 0 and another one is 1. This our bits will be in this two state only. But in quantum computing, there is one concept is basically called superposition. There, our states, all these states can be multiple times or multiple states at the same time. So here you can see that one, our quantum state, okay, and there is a zeros and one, both are there. Okay, so this is basically 2 qubit superposition. Okay, so here you can see that alpha and beta, this is the basically complex number or probability attributes, and then this our alpha square plus beta square should be 1. That means probability should be 1. In between it will be, and this is for alpha square is basically the probability of the qubit. If we measure this qubit, so what is the percentage of this presenting that state with the probability? So I think you know that measurement and all. Okay, so however I am discussing once that measurement. So whenever we will measure any particular quantum state, so we will get the exact, it is zeros or it is 1 with some probabilities. So how why we are not getting exact values? So whenever we are measuring any particular quantum state or quantum particles, so we are basically disturbing that particles. So whenever we are disturbing the particles, so it will not give the exact value. It will give the our values with some probabilities. Okay, so here you can see that. So what does it mean? So if I take it, so here you can see that. So our superposition state, I think you know, Dirac notation is like that. There's a two notation. One is basically called our called that. It's like that. So this is basically called Kate notation. Okay, Kate notation. Kate. And one more is there, that is basically, suppose 0, it is basically called the bra notation. Okay, so these are basically two basic notation. This is basically called the Dirac notation. So how can we represent this quantum superposition? So quantum superposition we can represent as like that. As we know that our classical bits either will be 0 or it will be 1. But in quantum computing, in this state, there can be zeros, 1, 0, 1, 0, like that. So this is basically called the superposition state. So in a state, the zeros and 1 can be in the linear combinations. Okay, so this is basically called linear combinations of zeros and 1. So this is basically called the superposition state. And whenever we will measure the suppose there is a 2 qubit system, that is 0 and 1. If we will measure this 0, so we will get that probability of zeros what is the probability of zeros to present in this state. So that only is saying here basically alpha square. You can see that alpha square is the probability of zeros to be there in this state. Okay, so similar to that, beta square is like that. So this is basically our superposition. Superposition is saying like that there can be linear combinations of zeros and one in a particular state. Okay, so how, or what is the advantage of that? We'll see later on this one. I think it's whatever I am discussing, it's gettable to you people. So maybe it is new to you, but these properties are very important for this quantum computing. So then we'll come to that entanglement. So what is entanglement? So entanglement means it's basically entangling or interconnecting the two qubits. Okay, there we have a lot of mechanism. There is a Bell state, there is a C0 gate to create the entanglement, and all. We'll see this later on. So this entanglement is nothing but if we will entangle the two qubits, then we can't separate it. It will be always entangled. Okay, as an example, I can say like that. Suppose you are seeing in your institute, two friends are always together. Okay, so if from backside you can find out one friend is that A, then you can automatically determine that with some probability B person is also there. So it is like an entangled state. So I can give you an example for that. So suppose there is a 2-qubit system, one is 0, one is 1. Okay, so first what we are doing, we are measuring this 0. Okay, if we measure it, we will get, suppose this is a 50% probability to get this 0. Then second one will be automatically determined. This next person is, or next qubit is 1. So it will be automatically determined. So if we will measure one particle or one qubit and we will get some probability, then next qubit will be automatically determined. So this is the concept of this entanglement. We can't separate it. We can't separately, we can't define it. Okay. So this is the concept of this entanglement. So next we'll come to this quantum computing. Why we require this quantum computing? So there is one concept is one advantage of this quantum computing over classical computing is like that parallelism. Okay, so how can we achieve the parallelism? So there is basically the superposition will help us to achieve this parallelism. So how can we we achieve this parallelism by superposition state? So suppose there is we have n qubits and there is a classical register can store n bits at a time. But whenever you will go to the superposition state, we can store their combination of 2 power n possibilities states. So whenever we will apply some quantum Fourier transform or unitary transformation, so our computation will be in the form of superposition. So at a time, one state, there will be multiple qubits. But in classical computing, only 1 or 0 will be processed. But in quantum computing, that total state I showed you previously, that one state 0, 1, 0, 1 like that, that total state will be processed at a time. Okay, so this speed up will be fast and it will be parallelly processed. So there is a 2 power n inputs can process at the same time. So this is one advantage of parallelism which we can achieve by this superposition. Then we'll come to that attacker detection or eavesdropping detection by using the entangled state. Okay, so suppose we are sending some information. So suppose we are sending some information to sender to receiver. So what will happen there? How can we detect it? So suppose there is a sender A and receiver B is there. So in between what the attacker can come, okay, and intercept that attack. So if we will send here 0 and 1, these two entangle bits and all, and in between if attacker came, and attacker will change this 0 as a 1 and this 1 as a 0, okay, and this entangle bit already shared with B, okay, and in between came and changed and again resend to basically B. So B already has this entangle state, okay, and this entangle state again resent by this attacker. So what will happen there, that this B will automatically get to know that this bits is changed there, or there is a double one, both are double one. So what will happen there, if this bit is changed, then automatically we will get to know by this our receiver that this bit is already changed by someone. So here what will happen, this this attack detection can be possible with this entanglement. And one more concept is there, that is basically called that our reversibility. So in the quantum computing, all the gates are reversible, okay. So in classical computer also, one gate is reversible, that is basically our NOT gate. So whatever input we will get as a give first initially, and whatever output we'll get, if again that output will give to that input, we'll get the same input whatever we have given. So I'll show you how its NOT gate is. Basically this is our NOT gate, correct. This is our NOT gate. If we'll give as 0, we'll get as a 1. Again this 1, if we'll give is here 1, we'll get it 0. So here our initial input was 0, we got again it's 0. Only this NOT gate is a reversible gate in our classical computing. But if you'll see that in quantum computing, almost all the gates are basically reversible gate. So here one gate is there, that is basically called C NOT gate. Okay, this is basically control NOT gate. Suppose there is a Q bit or Q bit state. So this is basically our control qubit. There is a two qubits. One is control qubit, another one is target qubit. So first one is our control qubit, second one is our target qubit. And whatever output we'll get, exactly A, whatever is there, we'll get it. And in this case, we'll get B XOR A. So here what will happen there, if you see the truth table of this one. So suppose we are giving there 0 0, control qubit 0, target qubit 0, and 0 1 1 0 1 1. If we will give it, so what will happen, we will get this output. And one more concept is there, that is basically called, if this control qubit is 1, then this target qubit will be flipped. So if you see that control qubit is 0, so nothing will happen, 0 0 will get, and control qubit is 0, then we'll get 0 1, and there is a target qubit is a control qubit is 1 1, then this target qubit will be flipped. So 1, this one is 0 is there, then it will be 1, and this is basically 1, it will be 0. Okay, if you will go through this logic also, same thing you will get. So if the C NOT gate concept is like that, if we will give control qubit as a 1, then target qubit will flip. Okay, so I think one more session is there for me tomorrow. I discuss in details of this C NOT gate, whatever gates are there. So here you can see that whatever input we are giving, for that output we are getting. Again, if this input to output will give to input, then we'll get the same thing. So this is basically called that reversibility. So what is the advantage of this reversibility? So in this classical computing or in classical form, we know the Moore's law. So Moore's law is saying like that each and every 18 months or 2 years in an integrated circuit, the transistor will be double. So there is a integrated circuit. If we will if the if in 18 months or 2 years the transistor will be double, so this transistor will become very closer of our circuit. So what will happen there, whenever transistor will come closer, then our basically gate will be more heat, or it will produce more heat. Basically our quantum gates are made using, or classical gates are made using by this transistor. Whenever this transistor will come very closer, so it will produce more heat. So whenever it will produce more heat, we will not get the our efficient result. So sometimes you can see that your earlier our computer was very big, like a one home, okay, or one room, like that. So right now we came to our computer as a laptop, then we are right now using tabs and all. So sometimes you can see that our laptop is going to be hang, or our you can see that our servers are sometimes producing so much heat and all, and we require to keep it in AC. Okay, so because of this problem, so it's each and every 18 months, and in a 2 years, in a integrated circuit, we need to almost keep double to get more efficiency and all. And whenever we are trying to get more efficiency or faster, it is basically producing more heat. Okay, so whenever it is more producing more heat, we are not getting the exact output whatever we require. Sometime our system is not producing proper result and all. So this is basically some advantage of our classical our quantum computer over classical computer. So I kept two quiz questions here. Okay. So can you give the answer of these questions? So which of the following key advantages of quantum computing? So you can do one thing. You can write in your text box, so that we'll get. Which of the key advantage I'm talking about? Irreversibility. It's not a. Basically, quantum computing is giving advantage of reversibility, not irreversibility. Okay. So parallelism, one thing, correct? So parallelism we can achieve by this quantum computing. We already saw by superposition we can achieve it. Okay. And next question is that two qubits are entangled when their states are independent of each other. Their states cannot be described independently, and they are in zero state together, and they are measured simultaneously. So I said that one example also I given. So what can be there? So there are possibilities is like that. Both the states, that is states we can't describe independently. If we are describing one state, then we have to describe the other one also. Okay, or either if there is a zeros and one, both the state we have to describe. Okay. So this is basically was that our general things. What is that our superposition and entanglement. Okay, so I think till now it's clear to you what is superposition, what is entanglement, and what is the advantage of quantum computing, why we are looking towards the quantum computing. Okay. So how can we achieve parallelism by using superposition and with that entanglement? And one more example I can give you. Okay, what is the basically in the form of cryptography or security? What is the advantage of that? Okay, so we in classical computing we have a very hard problem that is basically called discrete logarithm problem. Okay, so what is a discrete logarithm problem? So discrete logarithm problem is like that. Suppose there is a number is x power of in mod of P. Okay. So, so here we will get some result. Okay. So suppose I am taking one example of that. Okay. So 3 power 4, and if it is from the group of Z from 23, so what will get it here? Here we'll get it as 12 mod of um, 23. Okay, so it is basically 3 power 4 equals to 81. Okay, so if it is that, it is very simple and clear, correct? We can find out that if we give only 3 and power x equals to 12 mod of 23, can you find out this x? If our this prime is very small, basically very small prime is there, 23, then you can easily find out this one. Maybe 1-2 iteration is required for you, but it is very large prime. Like it's like 1, 2, 3, 5, 7, 1, and 2, 3. Like such kind of large prime is there. Okay, can you find out this x? It's very difficult to find out that things. So there will come that problem, factorization problem. So in classical computing, it's very difficult of this factorization problem. Do factorization of any numbers and all, very large prime or small primes, or that is very large number and all. It's very difficult. Okay, so this is basically called that discrete logarithm problem. So this problem cannot be solved within the polynomial time. This is basically NP-hard problem. But in classical quantum computing, there is a called short factorization algorithm, and this means this one, I think it will take 300 years like that. It's one statistics I saw to solve in classical computing. But in quantum computing, there is a called short factorization algorithm. It can easily do the factor of big numbers and all. So it's very high chance to eliminate this discrete logarithm problem. Till now, nowadays, we are using this discrete logarithm problem in our classical cryptography. Okay, whenever this discrete logarithm problem, whenever quantum computer will come to the picture, so by that time, this our discrete logarithm problem will be solved. So whenever this discrete logarithm problem will be solved, this whatever security system nowadays we are using, this RS algorithm, then Diffie-Hellman key exchange protocol, these protocols will be invalid. So there will be one very big threat for security also. Okay. So this is one more advantage of our basically quantum computing over the classical computing. Okay, so because of that only we are little bit moving towards the quantum computing. Okay, so it's after this FDP and this workshop, it should be clear to you, okay, why we are moving towards the quantum computing. Already we have high performance computer, and we have very powerful machine with us. Okay, so what can be threat this quantum computer will solve, whichever is not now solvable by our classical computing. So I think it's clear to you why we are moving towards this quantum computing. So these was the basic things about this entanglement, superposition, and all. I think it is also clear to you. So now I'll discuss one of my protocol that is published in IEEE transaction on intelligent transportation. Okay, so there I have used some quantum cryptographic protocols for securing the vehicular communication. So you can see that this is basically one vehicular communication. So there are so many vehicles are there on road. There is a roadside unit, and there is a traffic control center. This traffic control center, or you can say that traffic control system, So if there is some congestion or there is any accident, then this roadside unit will give the information to that our traffic control system. The traffic control system will give that information to the back vehicles and all. Okay, so this is the concept of this our vehicular communication. So this is the second. So what is the motivation of this vehicular communication, to provide that vehicular communication? So this motivation is simple. It's basically it can basically prevent the congestion or the accident, and there is a high cost of this communication cost as well as the computation cost, and there are some limited securities are there. If some attacker will come in between, and this they can attack in this way. Okay, so my main motivation was this design this protocol was to like that if this is a normal road like that, there is no problem for that. If it is a foggy highway, you can see that in Delhi side there will be a very high fog. Okay, even if you see that some cold countries like New Zealand, Switzerland, there will be very foggy highways. Okay, so what will happen there? If in front of any accident will happen, so backside vehicle will come and they will also collide with this front vehicles and all. So this is basically called our this is basically called rear end collision. Okay, so this collision, how can we avoid it? So for that we have so many mechanisms like that. Roadside units are there. It will send the information to traffic control system, and this traffic control system will send it back to that our back vehicles and all. Okay, this concept is clear. If this scenario will be our border side, like our Indo-Pakistan border, like it is Indo-China border. So this signal can be changed by the attacker. Maybe there can be so many our armed vehicle will be there. There will be so many army person and all, and their lives is very crucial for our country. Okay, so if we can provide the security in between the signals and all, then we can prevent some collision and all also. Their normal protocols will not work out. These signals can be changed by the attacker or intruder from some other countries. Okay, so that was my main motivation, to foggy highways give a strong protocol so that it can avoid the collision, congestion or accidents. So what is my contribution in this work? So there is this protocol is with low computation cost, and it is providing the some inside attack as well as some outside attack. Okay, so I discuss all those things, whatever the attacks are there. Okay, inside attack, what are the outside attacks and all. Okay. Then it can prevent foggy highway chain collision. So this is basically my designed protocol. Okay, so there is a TCS, traffic control system, or traffic control center, you can say. So there is so many vehicles are there on road, and this is totally foggy highway. Okay. So if some accident will happen to this first cluster and all or somewhere, so this TCS, what it will do, this roadside unit, all those things will send our signals to this TCS, and TCS will share that secret signal. That is basically we are calling that secret signal with that vehicle. So I'll see that setups and all. So here you can see that setups here. So traffic control system is there, and there is a secret signal is 0. Means there is no collision. 1 means congestion, and there 2 is collision. there is mostly probability will be congestion and collision. Okay, so this is basically setup of our framework. So here you can see that same things. There is a cluster. There is so many vehicles are there. We are given the name of that vehicles V1, V2, like VT, VN, and all. Okay. So this, suppose there is a congestion or collision. So their signal 1 will be give from here to TCS, or TCS will sense itself, and this TCS will distribute that secret signal to the back vehicle, so that back vehicle will not collide with this front vehicles and all. Okay. So how this TCS will share this secret signal? If it will give directly to that signal and all, so there also can be chance to interrupt it. Okay. So this sharing mechanism is basically given by a famous scientist, is basically called Shamir secret sharing. Okay. Shamir given one protocol, it's called Shamir secret sharing. So there is this one secret signal like one, that signal will be shared with this cluster of vehicles, and this, out of this cluster of vehicles, some vehicles can only reconstruct that original signal. If in total vehicles, here also we are considering this, some vehicles are corrupted or some vehicle will not give proper result, proper information. So what we are doing here, out of this n vehicle, we are taking suppose t vehicle to reconstruct that secret signal, similar to this our vehicles also. So what will happen whenever signal will give to this cluster of vehicles, this vehicle will reconstruct, okay, in front of that one, suppose there is a 0, means no collision is there. If 1 is there, there is a collision. This 2 is there, maybe 1 is there, that is for congestion, but 2 is there for collision. Okay, so backside vehicle will be alert, okay, some congestion or some collision is there in front of us, so we have to be careful. Okay, so that is from very VIP's vehicle as well as some armed vehicles. Okay, so in road on there will only not will be the VIP vehicles or armed vehicles, sometimes some local vehicles also will be there. That's why we have considered that T vehicles here, and this T minus N vehicles, N minus T vehicles we are considering as a corrupted vehicles. So this is basically our problem statement, and we have given this solution. So how we have given the solution? Okay, so for that we started some research work previously. So some research work was there. So this research work mostly was for classical computing, and their however their computation cost is more, and there was some critical security attacks was there, and it was not that much capable to give the privacy to the vehicles. So there we have used some quantum mechanism that is basically called quantum state. So I already discussed that quantum state. What is that? And superposition state also I have discussed. So there was a C0 gate. Okay, so this C0 gate basically I have discussed there. This is basically 2 qubit gate. One is control qubit, another one is target qubit. If control qubit will be 1, then target qubit will be flipped. If control qubit is 0, so it will not be flipped. And there is a quantum Fourier transform. So quantum Fourier transform is nothing but it's like our discrete Fourier transform. So it is basically linear transformation we are doing using this quantum Fourier transformation. Okay, and there is inverse quantum Fourier transform. So whatever, if we give one quantum state in the quantum Fourier transform, it will give us one more state, that is linear transformation state. And if that linear transformation state, if we give again back to that our inverse quantum Fourier transform, so it will give us that exactly whatever we have given that our normal quantum state. And there is a basically called Shamir secret sharing. So this is basically main mechanism which we have used here. Okay, So this summit secret sharing basically consists of two phases. One is secret sharing phase, another one is secret reconstruction phase. So how it's basically performing that secret sharing and all. So it is basically sharing the secret in the form of polynomials and all. Okay, suppose there is a secret signal 1, means in the road there is a collision. Okay. Yes, so what will happen there? So this one dealer will be there. Okay. So this dealer, what it will do? It will share that secret signal 1. So that is basically we are considering hearing as a TCS. TCS getting that secret signal 1 and it is sharing with that all the vehicles V1, then V2, like that, Vn. Like these vehicles it is sharing. So how it is sharing this TCS, what it will do? It will take a polynomial f of x, and this is a naught is basically this is basically secret signal a, and there will be a1 and x1 power a2 x2 like that. It is basically a n a t minus 1 and x t minus 1. So what is there here? T is basically threshold. We already showed that there is a T vehicles are there. So total number of our vehicles is N, and total number of vehicles are N, and T is the basically threshold number. Whatever the vehicles will consider for this reconstruction. Okay. So this T is basically will be degree of this polynomial will be T minus 1. Okay. So this is basically that polynomial with that secret will be shared. So I'll take one example of that so that it will be more clear. So suppose there is a f of x, secret signal is our 1. Okay. So there is a naught, a1. A1 will be random any number. So I am considering is a 1. Then our x values is there plus. Suppose t we are taking as a 3. So degree of this polynomial will be t minus 1, means x square. So if we'll consider again that a2 as our 1, then there will be a square t minus 1. So then whenever we'll share it with the vehicle 1, so this x will replace with the 1. So 1 plus 1 plus 1. So it is basically 3. So suppose here we are considering p means prime is taking as 11 like that. So here f of this is x1, if we take it f of x2, 1 plus this is x already we have taken, so we are considering as a x. So x will replace with this x will replace with values of 2 plus 2 square. Okay. So it is 4, 6, 7. Okay. So V2 will get 7. Like that will V till n will distribute. So out of this Vn will take only consider that till Vt vehicles. So here you can see that our reconstruction, whenever we have performed, so there is a total n vehicles are there. Out of this n vehicle, we are considering only the t vehicles to reconstruct it. So similar to that in the secret sharing. So what is happening there? The secret is sharing with all these vehicles with the degree of t minus 1 polynomial. Then what is happening in reconstruction phase? There is a t number of vehicles can reconstruct this secret signal. So this is basically concept of the secret sharing. Then this is the framework of our proposed protocol. Already we have discussed what is the framework. So we are considering there is a TCS or traffic control system or traffic control center. There's a secret signals, means 0 means no congestion, 1 means congestion, 2 means collision, and there is a group of vehicles cluster, and we are considering this is secure quantum channel. Okay. Then in this first protocol, what we are doing, we are basically TCS basically sharing the secret, which is congestion or not congestion, will sharing with the n vehicles, and it is basically encoding with the BB84 protocol. One encoding protocol is there, basically de-distribution protocol is there. Okay, so with that, and then we are transforming that that qubits to the n vehicles in the terms of secret signal. Okay, then what it is basically doing, it is using one hash function to create the secret signals hash values. Then that hash values again sharing with the n number of participants. Okay, that is the main work of this TCS, to share the secret signal with the vehicles. Now vehicles will perform the computation with themselves to reconstruct it. So there we have used that classical secret sharing reconstructions process. So what it's doing here is vehicle of the cluster VK compute the shares shadow. So it's basically computing the share shadows. We have given that lambda k as a name. So this k is basically t, total threshold number of players will be there. Okay, threshold number of vehicles will be there in the reconstruction process. And V1 we have taken that vehicle heads we have considered. So what will happen there, in vehicle heads will generate the t qubit particles which holds r qubits, and this is R is this in this form, and that vehicle will perform that quantum Fourier transform here on the particle of that, and it will, this quantum state will be like that. So whenever we will perform that quantum Fourier transform on this particular, so we will get the transformation like that. And then vehicle V1 again will generate the key qubit particles, and then vehicle V1 will execute the C0 gate in the particular LK state, and then this state will become like that. Okay. So already I have discussed this C0 gate, how it's basically performing. And then there is a general how the operator is basically performing by the each and every vehicles there, and then they are executing that Pauli operator on this phi 2 state. Then it is getting in this form, and then each vehicle VK perform inverse quantum Fourier transform on their particles, and it is broadcasting with the each and every vehicles, and that each vehicle cluster basically is summing up that their measurement result, and they are getting that secret signals. So they, right till now they have reconstructed that secret signal. Then one verification phase will come. Each and every vehicles right now got to know the secret signal, and what they are doing, they are that secret signals whatever they have reconstructed, that one will match with that they will create the hash values of this particular secret signal whatever they have got, and they will match with whatever secret signal that hash value shared by the TCS. If both are the equal, then they will consider that okay, this is that signal whatever we have got, it is correct or incorrect. If it is the correct, then they will take action according to that, or it will give the signals to that driver, or if it is automated vehicle, so it will automatically take that actions and all, and it will stop. If it is a other if it this two signals are not matching, then they will discard automatically that protocols. Okay, there is some mistakes and all, or there is a wrong signals and all is there, and according to that, vehicles will take that action. So this was that verification phase. Okay. So here I have discussed already with that some outside attack. So what is the outside attack? Outside attack, which attacks can be performed by the attacker from the outside. Okay. And some participant attack I saw. So if some vehicles, this attack is coming from inside the vehicles, if some vehicles are corrupted by itself, or they are not behaving honestly, and they are not giving the exact result or output and all, so what will happen then in this case? So this is basically outside attack we are considering as an intercept attack. Intercept attack is like that whenever we are sending some information or share shadow shares from the TCS vehicle 1 to other vehicles. So what will happen there? We are getting one particle, that is basically AFK particle, can be intercepted by this attacker. So whenever this attacker will intercept that F by K, our basically secret signal is in this shadow, secret signal shadows. So whenever this AFK getting by that attackers and all, with the probability they will get some values of F. Okay, but that is not the exact secret signal shadows, but secret signal shadows is our lambda k. So this lambda k is not getting, is getting some with some probability F values and all. Okay, so this attack is not possible here in intercept attack. So similar to that, intercept recent attack is there. If that signal this attacker is intercepted some signals and all, and it is sending back to the receiver and saying that okay, this is your original secret signals and all. So what will happen there? Whenever this particle already is entangled with another qubits and all, whenever I discussed in entanglement and all, so by that time whenever this receiver will get it, whenever receiver will check it, okay, this is that whatever sent by receivers and all, it not matching. So there is this particles are not correct, so it will discard by that particular receiver. Similar to this entanglement measure also, like that, two qubits will be, or two states will be entangled there, or particle will be entangled there, and it will match by the receiver. If it is matching, then it will keep. If it is not matching, then then receiver will think like that there is a entanglement, something changed by that entanglement and all, and whatever the sender previously sent that entangled one, that one will keep by that receiver and all. And there is a coherent attack. So what is doing in this coherent attack? So this attacker will basically attack that each and every particle of the basically that communication at the same time. So in this type also, if attacker will try to get the information, okay, it will get that X particle. Okay, so that X particle, and if it will measure it, they will give the X values with some probabilities and all. That probability is basically 1 by D. D is basically nothing but a prime. So it will not also not get the shadow of the share values. So similar to that collective attacks and all. So these collective attacks, the attacker will particularly go each and every qubit or our particles and all, and it will try to interact with each and every particles and try to get the information from there by the measurement. So it also will get that value X of Y, which is not relatable for this our shadow our secret signal shadows. So this attacks also is not possible there. Okay, so there another more attack is there, man in the middle attacks. It is basically similar to that our intercept attack. So same thing will happen here. F of K will be will get by the attacker, and it will, if it will measure that particular and all, and it will get only the f with some probability, but it will not get the exact values and all. So here also manning the medical attack is not possible. Then Trojan horse attack is there. So what it will be there? Attacker will try to attack with some kind of virus is basically to called Trojan horse. It will basically attack to that photons. Okay, so it is basically, it's called invisible photons and relays photons. So what it will do, it will try to hide that photons and all, or it will try to delay the photons and all. Okay, so it is basically try to maximum delays that signals and all, wavelength and all. If your channel is secure, or your whatever you are using secure channel, if you are using, so this attacks also, it's not possible for that. So this one was Trojan horse. Then is a participant attack is there. So participant attack is like that. If some of the vehicles will cloud together, and they will try to get some information of this SAT signals, and also how they can do it. Okay. So here also you can see that if this some vehicles will cloud together, they will get their with that their own particles and all. That is basically f of k. If they will perform the measurement of this f of k, they are only getting the f values with some probabilities and all, and they are not getting any values of this shadow signals. And there is a forgery attacks and all. Okay, so forgery attack basically we are preventing by using that hash function and all. Okay, so if both the hash values are matching, then only vehicles are considering that secret signal whatever sent by the TCS, it's correct. So here this SHA1 we have used for this preventing this forgery attacks and all. Okay. So there is a collision attack. So collision attack is very, very important attack in this when you are using any hash functions and all. Okay. So to reduce the quantum some computations cost, and also there we have used their SHA1 function, but there is in terms of classical computing, there is a less chance to get collision attack here. Okay. However, in after 160 bits, this our hash values will be generate. There will be some hash collisions and all. Okay. So there is if means traffic control system that hash value directly to that vehicles one, so there is a very less chance to get attacks and all. If it is a broadcasting, that it will be very high chance to get attacks and all. So what is doing here, TC is basically sending that secret signals hash values to the vehicles one. So this was about that collision attacks and all. So this is basically performance analysis. So whatever we have used, that is basically preventing that foggy highways collisions and all, and their computation cost and communication cost is low as compared to that our classical computing or previous sorts and all. Okay, so this was some quantum computing our protocols, existing protocol, and our proposed model was there. Okay, so here we showed that our protocol can almost prevent all this existing quantum computing attacks and all, as well as some classical computing attacks, and there are our computation cost. Okay, so here basically our computation cost is 1 whenever we are basically we are sending this our secret signal in the terms of this decoy particles and all. So we are basically computing one time that decoy particles to preventing these attacks and all, and one time we are performing that sharing and all. So because of that only our computation cost is less as compared to the existing protocols and all, and basically other protocols, they are basically computing that in time. Sometimes there's each and every vehicles is computing, so they are required for in time computation cost. So, and this is basically conclusion. So our protocol is secure against that outside and participant attack, and there is a low computation cost, and it can prevent the high foggy highways collisions attacks and all. So this is my references which I have used for my presentation, and existing some works is also there. Okay, so this is this was my presentation today. Okay, so if you have any question, you have a lot of time to ask from basics to advanced level questions and all regarding the quantum computing, so you can proceed for it. Do you have any questions regarding that superposition, entanglement, basic things about this regular communications, all those things? If you have any questions at all, you can ask. I'll be happy to give the answers of this.
Dear participants, it is a time for Q&A on this particular session. Kartick sir will be waiting for your valuable questions for this particular session.
At least I'm expecting some basic questions from this quantum computing.
Yeah, sure, sir.
So you can ask. What is the question?
Sir, Lakshman Rao Padala is asking why quantum computing will be requires cryptography, sir. Is one of our participants. Yes, sir.
Okay. Sir, I already discussed one problem is that in classical computing, there is one problem that is basically called discrete logarithm problem. Okay, so this discrete logarithm problem, if it will be solved, okay, then it's very high chance to get that attacks in this classical our cryptography and all. Okay, and some few more advantages there like entanglement and all. I already discussed that things and all. If some attack sender is sending some entangled state to that receiver sides and all for the quantum communications and all, if in between that attacker will come to perform that attacks and all, so what will happen there it will be detected there. If this attacker will change the any particular entangled bits in between, okay, so this for that changing that bits only receiver will get to know this bit already changed. Okay, so that detection will be there, attacker detection. Okay, so it is basically this entanglement will help to that to detect this attacker. More advantage is that superposition. I already said that things and all. If we required more high performance compute, more high performance, process we required for providing the securities and all, that will provide by that our superposition. Okay. So that is basically mostly required for this our quantum in our cryptography and all. And discrete logarithm problem, already I discussed what is the advantage of that. Okay, so it's if there is a there is if suppose there is a value of x and there is n and a mod of there is mod of something like p's and all, so we'll get some values and all. So if we know these x values, we can't find out, it's very difficult. If it is a big prime and all, this n values finding is very difficult for us. Okay, so it can be solved because of this factorization problem. So as we know that this discrete logarithm problem, basically DLP is basically NP hard problem. So it's very difficult to compute this our n values, okay, in classical computing right now. Whenever this quantum computer will come to that pictures and all, and we already have one protocol is called basically short factorization algorithm to factorize a very large integer and all. So whenever it will come to that picture and all, so it's this problem will be solved by our classical quantum computing. So then one problems will come there. Okay, so this because of that only, even some attacks, already quantum computing attacks is coming to that pictures and all. So because of that only, we required more quantum computing power as well as securities, like some quantum mechanics principles also, like superposition, entanglement, all those things is required for this our cryptography. So because of mostly that only, we are going towards this quantum computing for more securities and all. So till now we know that we have very limited resources for this quantum computing. So whenever these resources will come to us, it will be more clear to us uh, this advantage of cryptography. Till now, this quantum computing, it is in research level. Um, right now, Indian government just now launched the National Quantum Mission. Okay, so whenever it will more explore or more do research and all, few more advantage will come. So till now we know this theoretical advantage. Okay, so maybe in future we'll get to know that practical advantages are known also. How did this discrete logarithm problem will be solved in terms of classical cryptographies and all. Okay, so what would be that circuit for that, and all those things will be more clear to us in future. Okay, so till now we have this 2-3 points of this advantage of quantum computing in quantum cryptography. So even till now, quantum computing, as I saw, it explored little bit towards quantum machine learning, and it's mostly basically went to quantum cryptography, as well as our right now I'm seeing that our some description, some machine learning, deep learning also, this quantum cryptography coming to that pictures and so and till now not that much focused and all. Okay, so especially in the hardware side, we are seeing some limitations. So whenever it will come to more closer to us, okay, so it will be more clear, and in hardware level advantage what is there, and in application level advantage what is there. Okay, so theoretically some advantage we have, research level we got some advantage of that, and that's why we are using this one in our cryptography. That is basically we are calling right now and quantum cryptography. Okay, so if you see that this some protocols like that I discussed about Shamir secret sharing, correct? So there is a quantum secret sharing protocol already designed. Okay, so even this or security system, it is divided in three parts. One is basically cryptography, means whatever we are writing, that is we are writing in the form of secret. One more is there, it's called basically called our steganography. Steganography means whatever we are writing, we are giving one cover image of that particular secret. And one more is secure computation. So whenever the secure computation will come to that picture, this summit secret sharing and secure multi-party computation will come to that picture. So this secure multi-party Shamir secret sharing, already it is converted to quantum secret sharing, as well as this secure multi-party computation. It is also basically came to that secure multi-party quantum computation. So mostly this quantum computation means distributed computing securities. Whenever we are talking about this quantum distributed computing, so we are using this secure multi-party quantum computation. So what is there performing there in computation means we can compute anything like summation, like multiplication, and we can compare two numbers and all. We have one more problems in classical, that is basically called Millionaire's problem. If we have a two person A and B, A consists of some values of his net worth or some money he has, and B person also has some money and all. So without revealing their exact values and all, we can find out who is richer than whom. Okay, so this is basically called millionaire's problem. So if two millionaires are there, they have some monies and with them and all, and they are saying they are not agreed to share tell their exact values and all. They will share their whatever values are there with a number of players and all, or a number of computers and all. Okay, so we can compute from there securely that who is richer than whom. Okay, so this is basically mostly we are calling that multi-party computation. So there will be multi-party comparison. So there are very basic protocols are there. First came the quantum secret sharing, then came secure. Based on this quantum secret sharing, secure multi-party quantum computation came to that picture. Means there is a summation, then multiplication came to that picture, then comparison protocol. So whenever we can do compare of two numbers, like millionaire's problem, who is richer than whom, and that is securely, then we can do shorting also. Okay, so shorting, we are basically doing the shorting by the comparison only. So like bubble short we are doing, we are comparing the numbers and all, and we are basically comparing. So like that only, like March short and all. So such kind of shorts are basically there. Okay, so whenever we can perform the shorting and all, so then we can go for our voting, e-voting. So e-voting, what is happening there, we are basically whatever the that result we are getting, we are basically shorting that who is who got more vote and all. Like that we can perform that shorting also, voting also, and then we can apply it for auction. E-auction is there. So there is some more one is general auction is there, one is weekly auction is there. So people are basically using these protocols for this shorting protocol, voting protocol, and e-auction, such kind of protocols. So in this way only our quantum till now our cryptography means security system is going on. So I will not talk about that cryptography and all, because there is so many encryption technique, decryption techniques, all those things are there. So we are considering towards that quantum secure computation. Okay, and some people working on that quantum steganography also. Okay. So till now we are in this position of this our secret sharing. So some more basic things you can ask that things and all, like fundamental things, how our quantum bits are representing, we are quantum state, how we are representing. Okay, so later on it will be very helpful for you if you are going towards the research of these things, because you people already expert of this research, and also some of you. Okay, how quantum computing. In this teaching learning process, I have not more explored that things and all about this teaching learning processing, how this quantum computing will be helpful there. Okay, but it's like our some I can say that some whenever you require some more computations power and all. Okay, by that time I think it's required, but I have not exact answer for that. Application you can find out different if you a little bit go through the research areas and all. If you'll do little bit of more research on that, you will search some papers and all, you will get that in number of exploration of this quantum computing and all. If your basic things is clear, you can apply it to anywhere. These things we are taking one part as quantum cryptography, and some vehicular communication is one domain is there, and some other domain is like that healthcare domain you can apply there. There are also some security systems out there. You can design some quantum authentication protocol. Okay, so many of that you can see that this our my work there. One till now one problem statement is there. Okay, whenever I am taking that vehicles and all these vehicles are authenticated or not, I have not considered that one. I am considered everyone is authenticated. Okay, so there can one authentication protocol can be provided. So that is also open problem. Okay, like that you can apply to that group of institution of healthcare. Okay, like we have Apollo Hospital, correct? So this Apollo has mm, you know a lot of hospitals together. So suppose I'm going to do treatment of mine to suppose Apollo Chennai. I'm going. Okay, so then I somehow for my work and all I went to Apollo Kolkata. Okay, so there whenever I go there, I no need to carry this all these hard copies, scan copies, all those things. If I go there, if I am that authenticated resource person and all means patient and all, so what will happen there? If I my medical device means my mobile will be there, I can request to that author I am this our hospital authorities and all. Okay, you can provide me my our whatever that reports and all. So their authentication, all those things will be check of mine with my device and all, and they will send that in whatever the reports and all to me as well as to that hospital also. So in their authentication is required. So this authentication protocol, this quantum authentication is there. Basically, we can use this quantum authentication protocols and all. So such kind of applications we can use. Till now, I'm working in this vehicular communication and one medical domain, that is basically healthcare domain, and one more domain I started working in that our smart grid. Okay, so they are also in security. How can we provide that security in a smart grid and all? There is some aggregation function is required there. Means aggregate need to do that how much electricity, all those things producing by this our companies and all, and how much it is basically consuming by that our smart meters, all those things are there. So we can use this aggregation function in they are also smart grid. So these three domains are there in that is also security domain. I have went to the security domains and all, and I explored that things, and few more open is there. Quantum computing technology application in AI and NLP. Okay, so there I think you can one problem statement is there, that is basically drug discovery. Okay, so for this any particular disease, okay, so which drugs is required, all those things and all. Okay, so that for that you can go for that. So I saw that one quantum neural network came. Okay, and another model came, that is quantum graph neural network. So basically our that drug or gene structure, all those things are in terms of this our graph and all. So you can go for that graph neural network for drug discovery center. Okay. So I have not more explored in that AI NLP like that or machine learning like that, but I saw some applications of that. Okay. So you can use this one, quantum computing center. Till now, it is in initial level only. It's not went so far of this machine learning, and just people started doing research and all. Okay, especially you can see that these Chinese people and okay, mostly they are doing research on these things and all. So you just you can start of any topics, and you can apply this your quantum machine learning, quantum NLP, and AI also. However, frankly, I'm saying that I have not that much expertise on AI and NLP. I till now explored that's security and
Sir, thank you, sir. Kartick, sir. Thank you for.
Sir, you have any questions in quantum computing and all?
I have one question, sir.
Yes.
Sir. Sir, actually, vehicular network, you used quantum thing, quantum secret sharing, but how actually simulation is conducted in the quantum way? Like normal secret sharing, we use some coding, Python coding or something, but here the quantum secret sharing, what type of simulators are used, sir? I wanted to know, sir.
Okay, ma'am, you can do one thing. You can use that Python and QSkit code. You can QSkit package. You can use there. Okay, and there you will same thing whatever you was doing in classical computing. That coding you are doing, same you will do that in our quantum also. Like I have used there some C0 gate. So I have C0 logic I have implemented there. Okay, and there for this QSkit, if you will use, you will get more packages. Okay, like now we have created some package like secret sharing package, all those things we have created, and we are incorporating that things. So you can use that QSkit like Python and all. You can use it. Google Colab also you can use, and there you can simulate this one. Okay, but if you are talking about physical implementation, it is very difficult because as quantum computing power we don't have. Okay, so that things we have not did. Something we kept as our assumption. Okay, so that was our main thing.
Okay, sir. Thank you so much, sir, for excellent session.
Thank you, Deepa madam. Thank you for your valuable feedback. Thank you very much. Sir Kartick sir, your presence is more valuable and you delivered a excellent session, sir. Excellent session. We are receiving very good feedback from all participants and sir.
Thank you so much. Okay, basic things is fine, but I don't know how they understood that vehicular communication and all. No, it's basically new things for them and all. Okay, so maybe vehicular communication is fine for them, but quantum vehicular communication is new things. I heard that things.
Dear participants, we have one more session with Kartick Sutradhar sir by tomorrow, second session.
So tomorrow mostly we'll discuss about that quantum circuits and all. Okay, each and every gates I will explain how we are getting that matrix representation. Everything I'll discuss tomorrow, and mostly it will be hands-on only. Means I'll mathematically do everything, and if it will be better for you if you will sit with something. Okay, I know that it's very difficult time. Means 7:30 to it's basically everyone dinner time. However, if possible, you can do that some handwork also. Okay, so what it will happen? It will help you to understand more quantum computing, and it's we are talking about quantum, and all. If our basic things is not clear, it's very difficult to understand that what is going on exactly. So many packages are there, so many things are there. We can use it, but problem will be with us. Basic things we will not get to know how it's working, what is working, and all. Okay.
Yes, sir.
So
Yes, sir.
that is the very basic things and all.
Yes, sir. Yes, sir. Thanking you, yours once again. Thanking you, yours valuable presence, sir. And all participants are very much satisfied on this particular session, sir. Ma Ritika,
Yes, sir.
yeah, kindly.
Dr. Kartick Sutradhar, sir, thank you so much for sharing your knowledge and expertise with us today. Your presentation was informative and thought-provoking, sir. We appreciate the time you have taken to prepare and present this session, and your contributions to the field are truly commendable, sir. Your presence has enriched our faculty development program, and we hope to benefit from your experience in the future too, sir. Thank you again, sir, for your time and effort.
Thank you so much for giving me that opportunity to present my work in front of you and some provide some basic information about that quantum computing, and for that I am very fortunate for that. Okay, thank you so much for everyone. Okay, for joining and listening me almost 1.5 hour. Okay, 90 minutes.
Thank you very much, sir. Thank you very much, sir. Tomorrow also we are having one more session with you, sir.
Okay, sir.
We are
Okay.
participants are eagerly awaiting for your session, sir.
Okay. Thank you, sir. Thank you.
Thank you, sir. Thank you,
Okay,
sir.
sir.
Thank you, sir.